Hello everyone, in this video we're going to solve the January 23 of Physics Unit 1. I know I'm quite late to upload this video. Tomorrow is the exam, but I will try to explain as much as I could all the concepts for Unit 1 so that you can get prepared for your exams in the last minutes a bit much more better. So we are solving this paper. This is how you're going to write your name here and surname or other names over here. Okay, so let's start. Question 1. There are 18 questions, and I'll try to solve every questions with much detail, as much detail as possible. So for question 1, section A has obviously 10 MCQs. Question 1 says that which of the following is a scalar quantity? Scalar quantities are the one who only have magnitude and no direction. And magnitude is basically the meaning of numerical values, right? Magnitude, or in general word, it means that any quantity that has numerical values but no direction. And we can clearly see that displacement is involved with directions, so it is obviously not a scalar quantity. Moment, obviously this is a turning point of a force. Turning means direction is involved. Weight is again a type of force, and type of force means obviously direction is again involved with that. But power is the only quantity where force is where direction is not involved. It only has magnitude, and obviously any quantity that has only magnitude no direction indicates the category of that quantity. It is obviously a scalar quantity then, right? So option C is the correct answer. Which of the following describes gravitational field strength? Gravitational field strength mainly describe, if you just focus on the unit of gravitational field strength, it was Newton per kg, right? There are two G's in our unit 1 physics syllabus. One G represents gravitational field strength and another G was gravitational acceleration. The unit for gravitational acceleration is as simple as ms power minus 2, but the unit for gravitational field strength is kg, so Newton per kg. Newton means force and kg means mass, right? So in words, this unit can be broken down as a force per unit mass. Now, if you focus on all the options given in this question, weight per unit mass, always remember that weight is a type of force. So this kind of resembles with our definition, Newton per kg. So this is a force per unit mass. So it kind of resembles the statement that I have written on this right side, right? But still move on to the next parts. Acceleration per unit mass. No, this is not the definition. Gravitational potential energy, acceleration per unit weight. No, these are all wrong options. The first option is the correct answer. Newton per kg, force per unit mass, which means weight per unit mass could also be the possible answer since weight is a type of force. So option A is the correct answer. Moving to question 3. This one is a little bit in upside down question. Like in usually all of the questions, they always give an expression about mass was hanging from a spring, and because of the weight of the mass, the spring would extend, or the length of the spring would increase, right? Now this one was an example for compressive forces, right? A force that causes this entire length of the spring to get compressed. So if I just read out the question first and then point out the overall basic differences. The question 3 says that object of mass m is resting on top of a string. Focus on the fact over here that this time it is not hanging from the spring, it is resting on top of a spring, which means that the weight of the spring will be acting in the downward direction, which will cause the spring to compress, right? And the spring is compressed a further distance of delta x by a vertical force F, which is obviously the weight of the spring, which is clear to us up to this point. The force is removed and the spring returns to its original length as shown. Okay, so now they are saying that originally when there were no force or no F or no external forces were acting on the spring, this was the length of the spring. Okay, this was the original length, because they were saying that at first this one is figure 1, okay, and this one is figure 2. I'm just labeling this just so that I can explain the differences of the two figures clearly. Figure 1 was the situation when a force of F Newton was acting on the spring, which caused it to compress by a length of delta x, right? This is the compressed diagram. This is not the original one. This is the compressed length when a force F was acting on the spring. And on the right hand side, F2 is the original length of the spring when no force F was acting on the spring in the downward direction. So this is the original length. This is the original length. Now the question says that when the delta x becomes 0, the object has a vertical speed of v, which means that when you put that F Newton force on the spring in figure 1, it obviously compresses, and when you remove that force, obviously it's gonna decompress, right? From compressed to decompressed. And decompressed means that obviously it's going to decompress itself with a force, with a speed. So the velocity with which the spring decompresses is v over here. So which of the following equations describe the energy transfer as the spring returns to its original length? So if you focus on this one, they are specifically trying to find you the value for energy. The first energy that comes to my mind using the springs is work done. Right. For any kind of spring related questions, we are always focused on force acting on the spring, the like change in height, the change in extension of the spring due to the presence of force is obviously involved with work done. Because if you don't remember, the graph for force against extension, the area under the graph for force against extension will be a work done, right? We always assume it to be a triangular shape or like the linear shape, and the area is always half F into delta V. So the overall work done from figure 1 to figure 2 is half delta V. And now what are the two forces that are acting on this? Now if you focus on this part again, we are trying to find out the velocity, and the velocity is on the spring when the spring is moving from compressed state to the decompressed state, right? From figure 1 to figure 2, the spring wants to decompress itself, and that's when the spring has this speed, vertical speed of v, right? So when you want to find that, you are actually trying to focus on this figure 2. If you again focus on figure 2, the height increases. I mean, if you just consider this one as height from the bottom, if this is h, you can clearly see that after it decompresses, the value for h increases. So whenever there is an increase in height, the energy that is associated with increase in height is gravitational potential energy, right? So we can clearly see from the two diagrams that there is an increase in height. So increase in height indicates increase gravitational potential energy. There must be a change in GPE for the spring. And again, as the spring decompresses itself with a velocity v, velocity is also associated with kinetic energy. So the equation over here builds up to be work done. The total work done of this the total work done of this entire system is equal to the increase in height, that means equal to the gravitational potential energy, and increase in velocity, which is again equal to the kinetic energy, right? So you can say that GPE, gravitational potential energy, plus kinetic energy. Now if you just break down these equations, break down these quantities into broken equation format, work done is half force into delta x, just like I have explained previously from the graph that you are supposed to take the area under the graph. It is a triangular shape, so half base into height. And GPE is mgh plus ke is half m v square, right? I should actually rearrange this as this they are given in the question. Half f delta h and then half m v square, and then added with the height over here is obviously the change in height, and the change in height was clearly in the diagram you can see is delta x, right? The height from the compressed state to the decompressed state or the original length is delta x, right? So we can just write delta x in terms of in the space for h, so it is m g delta x. So you can clearly see that this resembles with the equation for option B. So option B was the correct answer. So this was the entire working for question 3. I hope it was clear for everyone. It was quite tricky, I must say. Let's move to question 4. A student measures the time taken for a steel ball bearing to fall a measured distance in the air. The student uses these measurements to determine the acceleration due to gravity. Which of the following conditions is needed to determine an accurate value for the acceleration due to gravity? The first thing that comes to my mind is that all these informations in the paragraph is totally useless because it is kind of a theoretical part of your unit 3, maybe experiment 1, yeah, core practical 1. The core practical 1 starts with the assumption that when we are trying to find out the acceleration due to gravity, we always assume that air resistance is negligible, right? Or the upthrust is negligible. So these are the like assumptions for all the equations of motions also. The 4 equations of motion that you study in our unit 1 kinematics, where the assumption for all those 4 equations was that air resistance is 0 or acceleration is constant, right? So in order to find the value for acceleration due to gravity, the assumption is going to be the same. Acceleration is constant, or air resistance is 0, or upthrust is 0, or like negligible, whatever term you want to use. So always whenever the question is associated with acceleration due to gravity or free fall, these are the 3 assumptions that are fixed for this kind of questions: that acceleration is constant, and thirdly was what is it, yeah, um, wait, I just explained it. Sorry, acceleration is constant, then yeah, air resistance were negligible. Yeah, sorry. AR means air resistance. Okay, air resistance and upthrust. Okay, AR and U means upthrust are negligible. So memorizing a little bits of assumptions and equations or explanations or definitions is very handy for your exams, because if you already knew this assumptions, like memorize these assumptions, then you would not be able, like you won't have to waste your time on option ABC. You could clearly understand that option D is the correct answer, right? Air resistance and upthrust should be negligible. It matches with our assumption we memorized in our unit 1 syllabus. So obviously option D is the correct answer. If you guys have any questions that why ABC is not the correct answer, please comment below. I will explain that in the comments. Question 5. A car is racing. So a racing car passes point P at a velocity of 35. The car accelerates uniformly after 5 seconds, passes point Q at a speed of 50 as shown. And which of the following expression gives a value for the distance in terms in meters given the 2 points? Okay. So the basic concept is that this is a like usual example for kinematics, from kinematics. They have given you the initial velocity 35, final velocity 50. If the time at point P was 0 and if the time at point Q was 5, that means the total distance, like the time taken to travel the distance from P to Q was 5 seconds. The total time for the distance was 5 seconds, right? So you have to find the value for S, and obviously the quantities that you are involved with, U, V, T, no acceleration is involved. So the equation should be S equals to U plus V over 2 over yeah, multiplied with T. And now you just have to make make this resemble with the options given over here. Option C would be the correct answer, because U plus V by 2 means that you can write it like this: half into U plus V and then multiplied with time. U plus V was 35 and 50, so 35 plus 50 multiplied with time was 5, and this is exactly option C, right? So option C is the correct answer for question number 5. So I think question 5 was very clear. Moving to question 6, it was about vector diagrams. Okay. A soap bubble is being blown by the wind. The free body force diagram shows the forces acting on the bubble. P is the force of the wind, W is the weight, and U is the upthrust. So these are the free body force diagram given over here. And which of the following vector diagrams shows the resultant force F acting on the bubble? So the first thing that comes to my mind is that in the vertical plane, there are two forces acting on the bubble, right? U and V. And again, I can clearly see that the magnitude of W will be greater than the magnitude of U because of the size of the length of the arrows. You can clearly see that the length of the arrow of W is much longer, much bigger than the length of the arrow for the U, which means that weight is greater than upthrust. So when you are trying to find the resultant force for the vertical direction, because when you are like trying to find the vector diagram, we always involve with like two dimensions, right? But they are like they are also giving you a values in two dimensions, but in one dimension they have multiple values, that is u and v in the vertical dimension or vertical plane. So you have to obviously find the resultant force in the vertical plane, and it would be w minus v, right? It will never be u minus w, it will be w minus v. Always the greater force always a smaller force will be subtracted from the greater force. Okay, so w minus v, so w minus u, not v, sorry, u. Okay, so now as we are going to ignore that the upthrust was there, we are gonna change, like do modifying in this equation, do some modifications. Wait, I do not have. Okay, there are so many colors but not white. I think this one will do then. Um, I'm just gonna erase this part that we're assuming. I'm just gonna use this diagram to make the final vector diagram. So that's why we'll erase this part and make this diagram look like this will be W minus upthrust. And now, as I always say for the vector diagrams, always try to draw the parallelogram. I think that the triangle method is very confusing for me, so I always prefer drawing the parallelogram. Parallelogram is that draw a copy for the force in the other plane or on the other side. That means for this downward force W minus V, draw a copy of that over here, and then again draw a copy for the P force connecting the two vertical lines. And always remember that all the lines should be parallel and of the equal length of each other, right? Obviously, as I'm not drawing a like scale diagram, so I'm not using that much of scales or protectors. But when we are trying to calculate measure scale diagram for vectors, then you have to keep in mind all these things, right? So this was a vertically downward, this was in this plane, this was P, this is again W minus U. Then we can clearly see that all the arrows, right, this was in this direction and this was in this downward direction. Okay, now we can clearly see that all the arrows kind of intersects at this part. Yeah, intersects at this point. That means if this was the origin or the starting point, right, then the final vector, resultant vector, will be from the origin towards the red dot, right, where all the arrows are connecting. So obviously they, sorry, okay, so obviously they give you a diagram in terms of a triangular shape, but now if you focus on the like triangular part of my diagram, you can clearly see that option B resembles with my triangular part. Okay, so as I was saying that we can clearly see that this part, okay, this part is resembling with the option B. That means option B is the correct answer for this question 6. So we will just write across over here, option B. If I again focus on the diagram, I hope the explanation for question 6 was clear. If it is not, if there is any question involved with question number 6, then please write in the comment section. We will move to question number 7. A person threw a ball vertically up in the air and caught the ball. A few seconds later, the graph of the vertical displacement time for the ball is shown. We can clearly see that from the point the ball was thrown, the ball was caught at exactly that point. That's why there is no vertical displacement, right? It reaches to a maximum height and then fall back to that same displacement. Now, this kind of graphs, always remember the displacement time graph is a resemblance for the actual pathway followed by the ball. Okay, so this is the actual pathway followed by the ball. We can clearly see that this is a double motion graph. That means that in the, like, if this is the maximum point, before maximum point the ball was actually moving in the upward direction, and after maximum point the ball was moving in the downward direction. And in the upward direction the ball doesn't actually accelerate, it decelerates, right? Because it was thrown with the initial velocity, but at maximum point the value becomes 0. So for the upward direction, if you just divide this entire journey to upward direction separately and downward direction separately, upward and downward, in the upward direction it has a initial velocity but final velocity is 0, right? It has an initial velocity of u but final velocity becomes 0, which indicates the object is not accelerating, it is decelerating, right? Because velocity has decreased, so object is decelerating. Or you can clearly say just minus a. And again for the downward direction, the journey starts from maximum point to the end of the journey, right? So from the maximum point it becomes the initial velocity then. So for the downward direction at the maximum point, initial velocity is 0 and final velocity is the velocity with which the ball hits the ground. So obviously it has a certain velocity, so there is a final velocity. And now we can clearly see for the downward direction velocity increases. Initial velocity was 0, final velocity has a certain value, so velocity increases, which means that the object was accelerating. Now for these kind of double motions, we always assume all the vector quantities in the upward direction to be positive and all the vector quantities in the downward direction to be negative. Like, this is the basic generalized assumption for everyone using the kinematics. Okay, for the upward direction, vertical components, like in these vertical directions only. Okay, for the upward direction we always assume all the vector quantities to be positive. For the downward direction we always assume the vector quantities to be negative. So we can clearly see that for the upward direction it will be plus minus a. This plus at the outside of the bracket indicates the direction, and eventually it becomes minus a, right? Using the basics of algebra, plus minus becomes minus. And again for the downward direction the object was actually accelerating, which will give it a value for positive a. But since it was accelerating in the downward direction, and in the downward direction all the vector quantities are assigned with negative sign in respect to their directions, so it will be minus a. And we can clearly see that for double motion, when we are working with upward and downward in together, you can clearly see that acceleration would be negative. Generalized, for generalized effect it will be negative, right? Even for upward it is negative, even for downward it is negative. So we assume for double motions that acceleration is negative for the entire pathway. Like, you do not need to write all these explanations in this MCQ answer. You just need to understand that for the double motion the overall acceleration is minus a, so which is option B, right? It gives you this is 0, that means below 0 is the negative axis, above 0 was the positive axis. And since the acceleration for the overall journey of the double motion was minus a, so option B is the correct answer. I hope question number 7 was clear. Moving to question number 8. A motor lifts a mass of 50,000 kg through a vertical height of 25. The motor has an output power of 700 kilowatt. Which of the following gives a time in seconds taken to lift the mass? So over here, whenever height is involved, that means we are obviously working with gravitational potential energy. So this line will give you GPE. Power can be broken down into energy over time. And if you want to just focus onto making an equation, GPE is also a form of energy. So if you just input that GPE into the space of this E, then you just have to make T the subject of the equation to find the value for T, or the expression for T. The equation would look like GPE is equals to power. GPE was 50,000 into G is like mgh, right? The equation for GP is mgh. So 50,000 into 9.81 into height was 25 and power was 700 kilowatt. 700 kilowatt means 7 into 10 to the power 5, or 7 with 5 zeros. So 7 1, 2, 3, 4, 5. Kilo means 10 to the power 3, right? So we'll just write 3 zeros in addition with 700. And we can see that this as a like resembles our option B. So option B is the correct answer. Moving to question 9, a student carries out an experiment to determine the Young modulus of a copper. The student adds known masses to a copper wire and measures the corresponding extensions of the wire. Known masses means that you already found the value for weight, or you can just calculate the value for weight using the equations of mgh. We do not need to measure the masses anymore because the masses are already known. So force is mg. And known masses and measure the corresponding extensions of the wire. The student was also measuring the corresponding extensions of the wire. Which other quantities should the student measure directly? Which means that if you just focus on the equation for Young modulus is stress over strain, stress is force over area, and strain is extension over length. And again, if you just break this down, it becomes force into length divided by delta x into area. And again, area is broken down into the formula of area, that is pi r square. So it can be further broken down into F into L divided by delta x into pi r square. We should also break down this force into mg, because we already understood that force was weight and weight was this mg. Now all the quantities that are actually being measured in this experiment to find out the Young modulus are this m, which was already known, this length, this extension, and this radius. Right, these are the four quantities that need to be measured that need to be measured in order to determine the value for Young modulus. They have already stated that mass was known, right? Known mass. That means there is no need to separately measure the mass. The extension was also measured, right? Measures the corresponding extension of the wire. So extension is also measured. That means mass and extension are already measured. You do not need to separately measure the mass anymore. The other two quantities that need to be measured were length and radius. That means obviously in order to find out the Young modulus, these are the two quantities the student still has to measure, right? So radius and original length of the wire, diameter and original length of the wire, and diameter and mass of the wire. So the problem over here is that we do not actually use this equation. We always use the equation, this one. We cannot actually measure the radius, right? We can measure the diameter, and from diameter we can measure the radius, that is r equals to d over 2, right? R equals to d over 2. So you always use this as d over 4, d square over 4. Like r, d over 2 whole square becomes d square over 4. This will give you the value for r square. Now, the two quantities that need to be measured for the student were original length, the L, and the diameter of the wire. So diameter and original length of the wire is option B. So option B is the correct answer. Previously, I wrote the area for the answer, like equation for the area was pi r square. You can also write it down as pi r square, but you cannot measure r. You can calculate r, right? There's a difference between measure and calculate. So that's why as a question wanted to find the other quantities that the student could directly measure, right? Measure directly, not using any equation. So the quantities that the student could measure directly were diameter and length, not the radius. Radius is calculated, diameter is measured. Okay, 9 is done. Moving to question 10. Two forces make a Newton's third law pair. Which of the following statements is true for these forces? Always remember the 5 statements for any two forces to be under Newton's third law pair. Okay, I will just write down the five statements. The forces must be of same type. Force must be of same type. The forces must be equal in magnitude. So equal in magnitude. 3. The forces must act in opposite directions. 4. The forces wait, equal in magnitude, must be of same type, must act on two different bodies. And lastly, 5, the forces must act according to a line, like creating a line. It's not going to work if the upper force is acting in this direction and the other force is acting in the downward direction. They must create a line of action, right? The two forces must create one line, or they must align with each other. So the forces must act with a line of action from same point. So again, if you memorize these 5 points, it would be easier for you to identify Newton's first law and Newton's third law pair. The only difference for Newton's first law pair would be the object act on same body. Right? All the values like one, criteria 1, 2, 3, and 4. So 3 and 5 would be same for Newton's first law pair forces, but for Newton's first law pair forces, option 4 would change. It would act on one different body, so one body or same body. But for Newton's third law pair forces, it must act on two different bodies. And again, from the memorizing part, we can clearly understand option B is the correct answer, because they are saying that they are the same type. Sorry, not option act on. Wait, they are the same type of forces that act on different bodies. They're the same type of forces that have different magnitudes. Yeah, option B is the correct answer, right? So from this explanation, we can understand that option B is the correct answer for question 10. So yeah, that's it again. We will move to section B now. Section A is done. Section B starts with a projectile. Okay. So they are showing that a stone is projected horizontally from a cliff. The initial horizontal velocity of the stone is 38, and the initial height of the stone is 12 as shown. Calculate the horizontal distance from the bottom of the cliff to where the stone hits the ground. Okay. So we need to find the distance in this, like the range, okay, from this part to this part. Maybe if you like continued this pathway, the stone would fall to this. So the horizontal distance traveled would be this one. Always remember that the projectile motion has two motions, like two directions, vertical direction and horizontal direction. So obviously it will travel a vertical motion and a horizontal motion. And regardless of the two motions, the time will be same for both vertical motion and horizontal motion. Now for horizontal motion, the object is moving with constant velocity, so we can only use the equation v equals to d by t. This is for horizontal constant motion. Okay. But again, for vertical direction, for vertical motion, you can use all the equations of motion, because for vertical motion, the object is accelerating at a rate of 9.81 meter per second, constant acceleration. Okay, all equations of motions can be used. Now, if you focus on this one, the question actually wants you to find the value for the horizontal distance. So you should be using the horizontal equation. But the problem is that we do not have the value for time. So we can calculate the value for time for the from the vertical motion. Okay. So for this entire scenario, we can clearly see that the ball was actually thrown in a horizontal direction. For this kind of scenarios, for this situation, the ball does not have any vertical component for the initial velocity, because it was not creating any angle. It was entirely moving in the horizontal direction, which means that the vertical component of the initial velocity was 0. The distance traveled, vertical distance traveled, was 12, and acceleration is obviously 9.81. This is not a double motion example, this is a single motion example. The ball is just falling downward, so acceleration is just 9.81. So we are going to do this maths using two parts. First doing vertical motion and then doing horizontal motion. So for vertical motion, you have the value for uv, which means the vertical component of initial velocity, which was 0, s is 12, a is 9.81. So we can clearly understand we have to use the equation s equals to ut plus half at square. Again, ut becomes 0 because u was 0, right? So it is 12 half into 9.81 into t square. So if you just make t the subject, it becomes 12 into 2 divided by 9.81, entire thing under a root. And if you calculate this, you will get the value of as 1.56 seconds. So this is the time taken for the ball to reach the ground, 1.56 seconds. And if this is the value for time, now you have the value for time. And again, if you focus on this part, horizontal constant velocity, it means that in the horizontal direction, for projectile motions in the horizontal direction, the object moves with constant velocity. It does not accelerate. It only accelerates in the vertical motion. The object moves with constant velocity, which means that even after traveling this much distance, when it reaches at this point, the horizontal component of the final velocity would still be 3.8. Okay, at every point the horizontal component of the velocity would be 3.8, because in the horizontal motion the object does not accelerate, it moves with constant velocity. So again, using this horizontal motion, this time v equals to d by t. You just have to make d the subject and it becomes v into t. V was 3.8 into 1.56, and if you just multiply it, you'll get the value, that is 5.94. But it is like, wait, sorry, it is recommended that you keep your answer as one decimal place, because if you go to the question, all the values are given in two significant figures, right? All the numerical values are given in two significant figures, so you should also keep your answer to two significant figure. So 5.9 meter is the horizontal distance traveled by the ball. Okay, 5.9 meter over here again. So this was the end for question number 11. We will move to question number 12. A student determined the viscosity of a liquid using the falling ball method. Okay, when the ball is falling at terminal velocity, the following equation applies: drag force equals to weight minus upthrust, and the density of the liquid was known. And the student used a balance and a digital caliper to make a measurements on the ball. Describe how the student could use her measurements to calculate a value for the drag force acting on the ball. So obviously you can understand, when the student was using a balance, that means the student was trying to measure the value for its mass, or the mass of the ball that was falling, right? And for a digital caliper means like vernier caliper or a micrometer screw gauge. They always measure the diameter of anything. Ball is a like circular shape or spherical shape, that means it has a diameter that can be measured using the caliper. So we will write our answer as: the student must measure the weight of the ball, and the student must measure the mass of the ball using the balance, and then calculate the weight using the equation W equals to mg. Okay, so I'll just write the answer and it will be clear for you all, like, I hope. The student measured the mass using balance. The student need to measure the mass using balance and calculate weight using W equals to mg. Right, now the student has a value for this weight of the ball. Okay, now the student just need to measure the value for the upthrust, or calculate the value for the upthrust, and input the values to calculate for the drag force, right? So now moving to the calculation for upthrust. For upthrust, the equation was rho Vg. They have already stated that the density of the liquid is known, right? Upthrust is always equal to the weight of the fluid that is displayed. Like, the upthrust acting on the object is always equal to the weight of the fluid that the object has displaced. Okay, so and ball falling method means, obviously the ball was falling inside a fluid in a measuring cylinder, so you could have easily measured the like volume, sorry, what is it, yeah, volume of fluid that has been displaced. Or you can also measure this using the equations for like volume of the sphere, and then density of the fluid, and then liquid that they are using over here, and the value for G is 9.81, right? So in order to calculate upthrust, you need to first find the values for rho, V, G. Now, G is obviously constant. Rho is also saying that they already know the value for density. And now if you break down this, the equation looks like 4 by 3 pi r cube rho g, right? R cube means over here that you need to find the value for radius, and obviously from our previous part we know that radius is not a quantity that need to be measured, it is a quantity that need to be calculated. We can only measure diameter, not radius. So in order to find the value for radius, we have to first find, like, measure radius, sorry, diameter of the ball. In order to calculate the value for radius, we need to measure the diameter of the ball. And again, I'm assuming that the ball is spherical, that's why I'm using the volume of the sphere, but it is not stated, right? I just broke this volume equation so that I could clearly explain that why are we measuring the diameter. Okay, so now to calculate the, like, sorry, they are using the caliper to measure the diameter. Okay, so using the diameter and using the, sorry, and using the, and using, wait, and using the caliper, measure the diameter. Obviously do not write in this region. And using the caliper, measure the diameter. Using this, measure the volume of the ball. Not measure, actually this time we are calculating the volume because the volume has a formula. So measure the diameter. Using this, calculate of the ball. Then finally, so not finally, then using upthrust equals to rho Vg. Since you have the value for volume now, rho was also already known, g is constant, you can calculate the value for upthrust. Right, so then using rho Vg, he can calculate upthrust. And once he has already the values for upthrust and weight, they just need to input this into the equation given over here, and the student could easily find out or calculate the value for drag force. Right, so this is it, the final answer for question 12a. Moving to part B. When falling through the liquid, the ball reached terminal velocity. The flow of the liquid around the ball was laminar, and calculate the viscosity of the liquid. Terminal velocity was this much, radius was this, and drag force was this. So we need to find the value for the, calculate the viscosity of the fluid. Viscosity of the fluid means obviously we're using the equation drag force equals to 6 pi r eta v term, right? So the main equation is v equals to 6 pi r eta v term. Eta is the viscosity, so we need to just make eta the subject, and it will be force divided by 6 pi r v term. Force is 1.1 into 10 to the power minus 2. 6 pi r is 0.5 into 10 to the power minus 2 again, and terminal velocity was 5.4 into 10 to the power minus 4. Okay, so if you calculate this, you'll get the value as 216 um, Pascal seconds, or you can keep your answer as a standard form, because all the questions, like all the numerical data, are given in the standard form to two significant figure, right? 5.4, 0.50, sorry, that is given in three significant figure, and then another one was 1.1. The least significant figure followed by the question was two significant figure, so you should also keep your answer in two significant figure. So 216 Pascal seconds can be broken down as 2.2, right? 2.2 into 10 to the power 2. So it is 2.2 into 10 to the power 2 Pascal seconds. So this is it, the end for question 12 also. I hope it was clear. Moving to question 13. Okay, a builder is making a path using uniform rectangular stones. A stone is resting A stone is resting horizontally on a step and is held in equilibrium by the builder's foot. You can clearly see in the diagram, like the stone was about to tip over in this direction, but the builder is making it rest on this situation by stepping a foot over here, right, by balancing all this turning effect. The center of gravity of the stone is at its center as shown. State what is meant by equilibrium. Equilibrium means obviously at the point where the forces are balanced, and since the forces are balanced, the resultant force would be zero, and at equilibrium, clockwise moment is equals to anti-clockwise moment, so the turning moment is also zero, right? The overall turning moment is also zero. So as they're giving you 2 marks, so you obviously have to write both the explanation for force and for moment. So at equilibrium, all the forces are balanced. So RF means resultant force. Okay, RF is 0. And not and actually, also clockwise moment is equal to anti-clockwise moment. So overall turning moment is 0. Moment is 0. Now this was a basic definition, I guess. Memorize it. It will be useful. State what is meant by the center of gravity of an object. Again, a definition: the point on an object from where the weight appears to act, or from where the weight acts. Right. From where the weight acts. So no explanations for part A. It was just definition questions. Moving to part B, the builder applies the minimum force P that will keep the stone in equilibrium. The position and direction of P is shown on the equilibrium, and complete the diagram above by adding labeled arrows to the positions and directions of the other forces acting on the stone. Now, if I draw this again over here, there was a step under this stone, right? And since the stone and the step are connected with each other, so there will be a reaction force coming from this step on this stone, right? So the reaction force will act from this part, like this is the force from this step on this stone, and obviously if there is a center of gravity, the weight will act vertically downward. This is weight and force from step on stone. Okay. And in this part, the stone has a weight of 415 newton, and the length is 0.9 meter. And we can clearly see that the distance from the other end to this step is 0.5. The center of gravity is at the center of the stone, which means that this part is exactly 0.4545 meters from the other end. And we need to calculate the magnitude of P. So if I draw the forces again, the forces were the force from the step of the builder was P in this direction, P. Weight was in this direction, W. This is P. And step was, like the force from the step was in this direction. This is, let me just assume this is as F. Okay. So now when we are trying to calculate moment, we have to always take the pivot from any point, right? So in my calculations, I will take the pivot from point F, because I do not know the value of that. So I will just take our moment from point F, or about point F. So this is always recommended that you always write this, that from which point you are taking your moment about. So taking moment about point F, which means that F is now moving as working as what is it? F is now working as a pivot. So weight is kind of making the stone move in an anti-clockwise direction about point F, and sorry, in a clockwise direction. Weight is making the stone move in a clockwise direction about point F, and force P is making the stone move in a anti-clockwise direction about point F, and the distance from the moment from the weight and the force, this direction from the weight and the force F is 0.05. How did I understand? If this length was 0.45, right? If the total length was 0.9, so you just have to divide it by 2. So it is 0.45 and the total length was 0.5, which means that this length was 0.05. We just need to subtract 0.45 from 0.5. So you get 0.05. And for this part, distance of P from F will be 0.4. From 0.9, you just need to subtract 0.5. It will give you 0.4. So now for that clockwise moment is equals to anti-clockwise moment. Anti-clockwise moment was P into 0.4 about from point F, and it will be weight was 415 into 0.05. So you just need to make P the subject. 415 into 0.05 divided by 0.4. And if you calculate this, you get the value as 51.9 Newton. But again, all the informations given in your questions are in like 3 significant, and the list is 2 significant figure, right? So you have to also keep your answer to 2 significant figure, because that is the least significant figure used in your question. So 52 is the correct answer. Question 13 is over. Moving to question 14. An engineer is designing a metal part of a machine. The part is in form of a cylindrical rod. The part is designed to behave elastically when compressive forces are applied, as shown. State what is meant by elastic deformation. Okay. Again, definitions. Elastic deformation means that when forces are applied, the object will obviously change its shape, but after the forces are removed, the object will return back to its original shape, right? So ability to return back to its original shape when forces are removed are known as plastic deformation. So these are this is actually the basic definition. Materials that return to their original shapes. Materials that return to their original shapes as the forces are removed. This is the basic definition. It was just 1 mark, no more details are needed. So this graph, a compressive stress strain graph for one material is shown. So for one metal is shown, and we can clearly see that the length is decreasing over here, right? And we have stress on the y-axis. So if you go back to this question, now they are saying that state the Young modulus of this material is about 2 into 10 to the power 11 Pascal. So again, if you have a graph for stress against strain, you are supposed to calculate the gradient, because stress over strain will give you Young modulus, and if you calculate the gradient for this graph, again the equation becomes stress over strain, so you will eventually get the Young modulus. Again, for this graph, it is a very easy to find out the value for the Young modulus from this kind of graph, because the graph is a linear straight line. But one of my students, Mansifa, has a very big problem trying to measure that how to calculate the Young modulus for stress strain graph using the graphs that are not exactly linear. For example, if the graph is maybe like this, so how is she supposed to measure the or calculate the Young modulus from this kind of graph? Then she have to use a ruler. Okay, then you all actually have to use a ruler and try to find out the linear part of the graph. How can you find the linear part of the graph? You just have to put the ruler over here and start to draw a line very close with the graph. You can clearly see that only these portions of the graph are linear, and after that portion the graph starts to curve down, which means that you have to measure the Young modulus from this linear section only. So we have to measure the Young modulus from the linear sections only and not from the non-linear sections. This is how you identify the linear sections from a non-linear graph. Okay, so again, this was not related to this question, just a basic problem. So now to find out the gradient for this graph, you can easily find the gradient if you just focus on this part, this point. This point is approximately, not approximately, exactly at 4.4, right? 4.4, 10 to the power 8 Pascal. And again in the horizontal, on the x-axis, it gives you 2.2 into 10 to the power 3 strand. So when we are trying to find the value for Young modulus, you just have to divide 2.2 by 4.4 and you will get the value for Young modulus. Okay, so Young modulus is 4.4 into 10 to the power 8 divided by 2.2 into 10 to the power minus 3. You get the value as exactly 2.2 into 10 to the power 11, so which is totally fine. 2 into 10 to the power 11 pascals. And now the metal part must not compress more than 0.6 millimeter when a force of this much is applied. We need to deduce that if the metal is suitable for this part. So we were working for a certain like mechanism for a machine, and the instruction says that the machine must not compress more than 0.6 millimeter. So we need to like calculate that even after applying a force of 9.5 on this material, which has a Young modulus of 2 into 10 to the power 11, is the extension or compression is 0.6 or not. Compression or extension can both be assumed as delta x for the Young modulus questions, right? So as we have already found the value for Young modulus, that means now we need to use that for this part 2 somehow. So the equation for Young modulus was Young modulus equals to stress over strain. I'll just break down the derivations first and then input the values. It will be very easier to explain in that way. Stress over strain. Again, Young modulus, stress can be broken down into force over area, and strain can be broken down into delta x over L, which is eventually F into L divided by area into delta x. Now if you just make delta x the subject, the equation looks like F into L, the force applied on the material, the original length of the material, the area, cross-sectional area of the material, and the Young modulus of the material. If you just input all the values, you will get the value for extension. So you actually have all these values also. So delta x would be force 9.5 10 to the power 5. So 9.5 into 10 to the power 5 multiplied with original length 0.84 divided by area 4.8 into 10 to the power minus 3, and the Young modulus that we calculated in part 1, that was 2 into 10 to the power 11. So 2 into 10 power 11. Now if you calculate this, you will get the value as meter, because you can clearly see from all the parts every unit is in meter, right? But the extension must be figured out in millimeter, so we will just convert this later to millimeter, which we can do by dividing this entire amount, sorry, not dividing, yeah, by dividing this entire amount by 10 to the power minus 4. So if you calculate this, 9.5 into 10 to the power 5 into 0.84 divided by 4.8 into 10 to the power minus 3 into 2 into 10 to the power 11, you get 8.31 into 10 to the power minus 5. Sorry, you need to multiply it with 10 to the power 4, not minus 4. Okay, And when you multiply it with 10 to the power 4, you get 8 point, wait, 8.325 into 10 to the power minus 4, and then multiplying with this gives you 8 point, maybe I made a mistake in calculations. 9.5 into 10 to the power 5 multiplying with 0.84, 4.8 into 10 to the power minus 3, 2 into 10 to the power 11. If this is in meter, 8.321 is in meter, then for in millimeters you have to sorry, I made a mistake. For conversion of meter to millimeter, you have to multiply 10 to the power 3. Okay, from meter to millimeter, you're supposed to multiply 10 to the power 3 and you get a value of a 0.83, which we can clearly see is greater than the 0.6 millimeter, right? So we can see that when a force of 9.5 into 10 to the power 5 was applied on the material was compressed over 0.83 millimeter, which is greater than 0.6. So this kind of material is not suitable for making this machine or making this metal part. So you have to then write down the answer that 0.83 millimeter is greater than 0.60 millimeter. So not suitable. Right. This is for part 2. So questions 14 is over again. I hope it was clear. Moving to question 15, we only have 3 questions left. Sorry, 4 questions left. Sorry. Okay, question 15. A gymnast bounces on a trampoline. For part of each bounce, the gymnast is in contact with the trampoline for the rest of the for the rest of each bounce, the gymnast is in air. Okay, as shown, the trampoline gives the gymnast a maximum upward acceleration of 14.2. Calculate the maximum upward force of the trampoline on the gymnast. Mass of gymnast is 58 kgs. This is basically the reaction force from the trampoline, right? When the gymnast is in contact with the trampoline, only when the trampoline will exert a force on the gymnast, right? So when the gymnast is at this point, when the gymnast is in contact with the trampoline, then weight acts downward and the upward force, this is the trampoline. I should make it an accurate diagram. The weight acts downward and the upward force is the like maybe force P, right? So we can clearly say that there are two forces acting in the vertical plane. So we have to use the equation now, resultant force, and since the object is accelerating, so resultant force equals to mass into acceleration. So it becomes RF MA. Now RF is the overall summation of the two forces, but as they are in opposite direction, they will get subtracted. And again, we can clearly see that the object was accelerating upward, which means that the upward force must be greater than the downward force, since it was finally accelerating in the upward direction. So it means that upward force from the trampoline, that the reaction force from the trampoline was greater than the weight of the gymnast. And weight can be broken down into mg, so P becomes ma plus mg. So it becomes 58 into 14.2 plus 58 into 9.81. So if you calculate this, you'll get the value for the maximum force exerted by the trampoline on the gymnast, which is 1.39 into 10 to the power 3. But again, there are like two numerical equations, two numerical value, 3 significant and 2 significant figure. The least is two significant figures, so you're supposed to keep your answer in again two significant figure. So I will write the answer is 1.39 into 10 to the power 3 Newton or kilonewton, and you can also write your answer as 1.4 into 10 to the power 3 Newton. I'm keeping my answer as two significant figure because the question uses two significant figure as the least SF significant figures. So this was the solution for 15A. Moving to 15B, the trampoline is made of a sheet of material attached to a frame by springs. The vertical component of the tension in the spring provided the upward force on the gymnast. The vertical components of the tension. Okay, now the vertical component of the tension on the spring is 68 when the spring makes an angle of 14 degree to the horizontal as shown. Obviously, we know there is a vertical component and horizontal component. This becomes t cos 14. This becomes t sine 14. And since they have already given you the value for the vertical component, that was 68, and now they need to find out the value for the actual t, so we can just make an equation t sine 14. This was the vertical component, which was equal to 68 because they have already given you the value for the vertical component to be 68. So you have to just make t the subject, and it becomes 68 divided by sine 14 degrees, and it gives you a value of 281. So 281 Newton, right? And the extension of the spring was this much meter. We need to calculate the stiffness. Stiffness means the spring constant or K. So we have to again use the equation of F equals to K delta X. So as we are trying to find out the value for K, I will just make K the subject from the start. Force was force divided by delta X. Force was 281, the tension in the spring, and extension was 4.86 into 10 to the power minus 2. And again, if you calculate this, you'll get the value as 6.11 into 10 to the power 3 minus 3 Newton, so just 3 Newton per meter. So this is again the end for part 2. For part C, this is a star mark question. That means your writing pattern will be judged for these questions. Most of the people don't get full marks, and we all when you are checking your own paper, it is always recommended that you do not measure that you got all 6 marks for these questions, right? When you're like self-checking, like self-practicing, you always assume that you would get at least 5 to 4 marks. Never give yourself 6 marks. It just like helps you keep your expectations as low as possible. Okay, so this kind of questions, obviously your writing pattern will be judged. So let's start. The vertical acceleration of the gymnast varies while she is in contact with the trampoline. Now the acceleration is not constant, right? At every point the acceleration changes. The first line says that. Explain how the forces on the gymnast affect the vertical acceleration while she is in contact with the trampoline. Like obviously if the acceleration is changing, that means the forces that are acting on the gymnast are also changing at every point, and you need to explain that how those forces are changing that causes this change in the acceleration. And your answer should identify the forces acting on the gymnast and the direction of the forces. You're obviously supposed to ignore the air resistance. Okay, so at first we need to identify the forces that are acting on the gymnast. From the first page, we did identify the forces, right? The reaction force from the trampoline and the weight of the gymnast, right? These are the two forces that are acting on the gymnast, and because of these two forces, the acceleration will change. Now, always remember that normal reaction force always acts on a person or on a thing as long as it is in contact with the object, right? For example, the normal reaction force from the trampoline will only act on the gymnast as long as the gymnast is in contact with the trampoline. Now the problem is that the gymnast doesn't, like, for the entire journey while it is jumping in the vertical direction, the gymnast is not in contact with the trampoline. The gymnast lose contact from the trampoline, and as gymnast is moving in the upward direction, she loses contact. So in the upward direction, the value for the r decreases, which means w becomes greater, and when w becomes greater, the object start like in the upward direction, the value for its acceleration begins to decrease. But again, when it is falling downward, it eventually comes in contact with the normal reaction, like in contact with the trampoline. So normal reaction force continues to increase as long as a contact becomes more stronger between the trampoline and the gymnast. And when R becomes greater than weight, then the resultant force in the downward direction is great. So the object is accelerating in the downward direction, or the object will be, or the acceleration of the gymnast will increase, right? These are the two scenarios. If I just explain this in the blank page, we had a blank page, yeah, there's a blank page. The first scenario, like the overall jump looks like this. On trampoline, moves up, reaches maximum height, moves down, then comes back in contact with the trampoline again, right? So what happens in this upward direction, the object, sorry, the not the object, the gymnast, she loses contact from the trampoline. So the value of R, normal reaction force, from the trampoline to the gymnast decreases. So there are two forces acting on the gymnast in this half of the journey, weight and R is smaller. For this part, I'm intentionally writing the value for R as, like, the arrow for R as small, because I'm assuming that as the gymnast tries to move in the upward direction, the gymnast will lose contact with the trampoline, so normal reaction force will decrease for the upward direction, right? So as we can clearly see, the weight will be greater than the normal reaction force. So for this one, acceleration is in the downward direction, or we can say that the object would be decelerating, or gymnast would be decelerating. And when the gymnast again falls onto the trampoline, the contact between the trampoline and her foot becomes starts to increase. And when the contact starts to increase, the normal reaction force again starts to increase. So this point, the weight will be smaller, like weight is still same, but normal reaction force will be greater. And for falling, when the normal reaction force becomes greater than weight, the overall acceleration is greater in the upward direction, right? Or the acceleration is now in the upward direction. So this is in A, upward direction, A, downward direction. This is how the acceleration changes over the journey for the gymnast. So now we need to write this in good English so that we get marks. So the writing part starts with that when the gymnast bounces on a trampoline, multiple forces are acting on her, right? The multiple forces are weight and normal reaction force. So actually, I will not waste time writing this. I will just, okay. So this is the written answer for 15C. So it says that when the gymnast is bouncing on a trampoline, various forces act on her. The weight of the gymnast acts downward, and the normal reaction force acts upward, right? Sorry, acts upward. And as the gymnast moves upward, the normal contact force decreases. As she moves downward, it increases. At the bottom of the bounce, the normal contact force is at its maximum, and the normal contact force becomes zero when the gymnast loses total contact with the trampoline. So the resultant force acting on the gymnast is the difference between her weight and normal reaction force, right? Like RF is equals to R minus W. And we are going to use different equations for different situations. When it is moving in the upward direction, then the equation will be R minus W, because in the upward direction resultant force is greater. Sorry, I made a mistake. For the upward direction, resultant force is smaller, so it will be W minus R. For the downward direction, it will be R minus W, because resultant force was greater, right? So this was the explanation for 15C. If you write the equation, this is W minus R, and this will be R minus W, right? Just this explanation was written in good English in the 15 part C. So I did not waste any time over there. We will move to question 16. A spaceship is used to make astronauts and equipment in the International Space Station. The spaceship consists of an orbiter module, a descent module, and a service module as shown. orbital, descent, and service, right? The astronauts return to the Earth, to Earth in the descent module. So this is the one where the astronauts return in. The orbital module and the surface module move away from the descent module in the opposite direction as shown below with their speeds respectively. We need to determine the velocity v of the descent module after separation. We have to take only horizontal line of actions, not any angular momentum concerned with this. So for horizontal line of actions, as we do not know that in which direction d actually moves, I'm going to assume that d moves in towards the direction of s. So if my assumption is correct, the final velocity of d would be positive, and if my assumption is not correct, then d would be moving in the like in the direction towards O, and the final value for D would be negative. Okay, so I'm assuming that D is moving towards S, and so we are taking the measure we are taking the direction towards right as positive. Okay, so I have to write it down over here again. Taking right as positive, and I am assuming that D is moving towards S. Sorry. Okay, so as I was saying that the equation would be now, as I'm assuming that D is moving in this direction, so D and S are going to be in the same direction or same side, and O would be in the other side, right? So it will be the mass of S is 2100 into 0.58 plus mass of D is 2950 multiplied with V, we do not know the value for V, equals to 1350 into 0.82. So if you just make V the subject, 1350 into 0.82 minus 2100, 0.58, 2950. And if you calculate this, you'll get the value for the final velocity, which is 0.037. Okay, 376. But again, the least significant figure is two significant figure. Wait, 0.58, 0.8, 33, 33, yeah, 21. So two significant figures. So 0.0376 is the actual one, but we will keep our answer to two significant figure, so which is 0.04. The problem is here that it comes as a negative value over here, negative 0.0376, which means that my assumption was wrong. D was not actually moving towards S, D was moving towards D. And as my assumption was wrong, this negative sign proves it, right? So direction would be towards O, towards O, orbital, what is it, orbital module, right? Okay. So this was the solution for 16A. Moving to the B part, the velocity of the descent module can be changed using a rocket motor. The rocket motor ejects hot gases at high velocity. Explain how the velocity of the descent module changes when the rocket motor is used. We have to refer answer using Newton's law of motion. Okay, again, think of it like this. When the rocket is ejecting ejecting gases, the rocket is providing or exerting force on the gases, and as Newton's third law pair forces, the gases will again exert a force in the rocket, on the rocket. Now this force exerted by the gases on the rocket will act as a resultant force for the rocket, and again according to Newton's second law, due to the presence of resultant force, the object or the what is it descent module will now accelerate, and acceleration means that the velocity of the module will change now, right? So this was the explanation, just a 3-mark question. I will just again write the answer again. Okay, so here is the explanation. It says that when the rocket is ignited, it provides a force on the gases, and as a result, the force will exert an equal and opposite force on the rocket motor itself. And according to Newton's third law, the third law of motion, which states that every action is equal to every action, sorry, where is it, every action there is an equal and opposite reaction, right? It is always suitable that you write the law over here also. Okay, so this reaction force for on the rocket, so this reaction force on the rocket produces a resultant, just skip this, resultant or net, just resultant force acting on the descent module of the rocket. According to Newton's second law, the motion, this unbalanced force results in an acceleration of the descent module, right? So this is the answer, but the main explanation was the one I given in the start of your question, right? So this is part B1. Moving to part B2, and they need to find the, sorry, when the rocket motor is operating with the velocity of the descent module changes by 0.58 meter per second. So this is the value for change in velocity. The time is also given, the mass is given. You need to find the value for force. So you can use the equation for F equals to ma, where a is broken down into change in velocity over t. So mass is 2950, 0.58, time is 5. Now if you calculate this, you'll get the value for mass of the descent module, which is 342.2 Newton. Okay, so 342.2 Newton. And again, if you move to this question, the least significant figure was 1, 5.0. This was the least significant figure, so you should also keep your answer to 1, sorry, 5.0 is 2, sorry, 5.0 is 2 significant figure, so you should also keep your answer to 2 significant figure, so it will become 340 Newton, right? 340 newtons. Question 16 is done. Moving to question 17. In a game called High Striker, a person hits the button with a hammer. This causes the cylinder to move upward. The bell at the move towards the bell at the top as shown. So the hammer will hit this cylinder, and the cylinder will eventually move this height and hit the bell at the top. So this is the entire mechanism for this high striker. The question says over here, part A, the kinetic energy of the hammer head as it hits the bottom is greater than the change in gravitational potential energy of the hammer head as it moves down. We need to explain why that the amount of kinetic energy that is provided to this hammer is greater than the gravitational potential energy of the hammer itself. So you have to understand that gravitational potential energy is only associated with the increase in height or decrease in height, right? So the decrease in height is over up to this point. The hammer is just going to travel a height of this much distance, right? Now, but the entire work done is always equal to Ke plus GPE, right? Work done is always equals to kinetic energy and gravitational potential energy. And as GPE cannot change, the height, like GPE is measured in mgh. Mass is constant, G is constant. For this situation, H is also constant. The height traveled by the hammer is H. So entire GP is constant. But if you broke down work done, that is FD, and kinetic energy is mv square, half mv square. For this situation, the force on the hammer is just not the weight of the hammer. This time the person is also providing a force on the hammer, right? Because the person is doing the work. So there is a force exerted on the hammer by the person, and due to this, the hammer is not in free fall. The hammer is not in free fall indicates that work done is now greater. So if work done increases, the kinetic energy not needs to increase, because gravitational potential energy is a constant variable, right? If you just focus on this one, gravitational potential is a constant variable. If work done increases, the right hand side of the equation also needs to increase, and as the one part of the right hand side of the equation, GP is constant, so an increase in work done will obviously cause the kinetic energy to increase, right? So that's why for part A, the kinetic energy of the hammerhead is greater than the gravitational potential energy. So we need to arrange our answer again as according to the equation. So not according to the equation, the hammerhead is not in free fall as the person is exerting a force on the hammer, right? is exerting force on hammer? Is exerting force on hammer head? Right, so the work done this time is greater as the person as sorry, as the work done is greater as the person is exerting force. Exerting force. Now again, as the height traveled is not sorry, as the height fallen by the hammer does not change, so GP remains same. That's why KE needs to increase, right? So GPE is constant to balance out. KE must increase. Okay. So this is for part A, the explanation and the written answer for 17A. So we will now move to question 17B, where it says that the hammer is initially at rest, and as it at its highest point, as the person moves the hammer head towards the bottom, towards the button, the average resultant force on the hammerhead is 58 Newton. The hammerhead moves a distance of 1.2 Newton before hitting the button, and the cylinder moves 2.7 meter, so it must move 2.7 meter upward to hit that bell at the top of that striker thing, right? So we need to deduce that if the cylinder actually hits the bell. So they have also said that the mass of the cylinder is 0.15 kg and the efficiency is 4%. So the main concept over here is that the weight of the hammer is 58 Newton and the height, this h, right, this h is 1.2 meter, and the entire work done by the hammer, like only 4% of that work done or energy is transferred to the cylinder. So the entire amount of energy is not transferred, only the 4% of that energy is transferred. So on with that 4% energy, can the cylinder rise a height of 2.7 meter or not? We need to like measure that, like we need to actually measure the height increased by the cylinder. Okay, so we can measure this by using the equations. First we need to find out the energy of the hammerhead, right? Energy provided by the hammerhead. So energy of hammer, which would be since the equation over here uses weight and for and distance, so we have to use the equations of work done, F into D, right? F into D, which is 58 into 1.2, which gives 69.6 joules. And again, as the efficiency is only 4%, that means out of this total energy input, only 4% will be the useful energy output. So energy output is 4%, 4 over 100 of this 69.6 joule, which is 2.78 joules. And finally, we need to find the gravitational potential energy, which is obviously this, because the cylinder increases its height, right? So which means that this is the energy, gravitational potential energy of the cylinder. So we can say that GPE of cylinder, which is 2.78, GPE is mgh, is equals to 2.78, where h is the height and we need to find the value for this h, right? So it is 2.78, mass was 0.15 and g is 9.81. So if you calculate this, you'll get the value as 1.89, or one decimal place it will be 1.9, right? One like two significant figures. 1.9 meter. We can clearly see that the height reached by the cylinder is less than the 2.7 meters. So yeah, obviously the cylinder does not hit the bell at the top. Okay, so just write the statement over here that 1.5 meter is less than 2.7 meter. So cylinder does not reach the bell. Again, finally at C, it says that if the velocity of the hammerhead as it hits the bottom doubles, the height gained by the cylinder does not double. We need to explain this and why it is the case. It is because velocity and height are not exactly directly proportional, right? This is like in this situation, kinetic energy is equals to kinetic energy is equals to mgh. Now if you break down kinetic energy, the equation is ke equals to half mv square. So when v is double, like when velocity is doubled, ke equals to half into 2v, like m 2v square, which means that the overall velocity will increase by 4, right? 2 square is 4, so the kinetic energy will also increase by 4 times. So when velocity increases by 2 times, kinetic energy increases by 4 times. And as kinetic energy is directly proportional or equal to gravitational potential energy, if kinetic energy increases by 4 times, as mass and gravitational acceleration are constant, so obviously height also needs to increase by 4 times to balance everything out, right? Ke needs to increase by 4 times, so h also increase by 4 times. So we have to write it down over here as ke, kinetic energy, is proportional to the square of velocity, not just velocity, square of velocity is proportional to v square. So when v doubles, ke increases by 4, by 4 times, and as ke is equals to gpe, when as k is equals to gpe, height increases by 4 times also, right? By 4 times. This was the actual answer. The other parts were just for the explanation working. Okay, so we are now going to the last part of this question, question 18. It says that an object of mass 35 kg fell from a boat to the seabed, like at the bottom of the sea. The object reached terminal velocity as it fell, so that the drag force acting on the object at terminal velocity was about 200 Newton. The volume is given and the density of the seawater is also given. So obviously we're using the same equation given in our maybe question 11 or 12. Drag force is equals to weight minus upthrust. Okay, and why are we using this? Because they were saying that it was falling downward, right? Which means weight was greater than upthrust, right? Weight was greater than upthrust, and again, since it was falling downward, drag will be always against the motion. So d is also in the upward direction, so it kind of becomes u plus d equals to w. But as we need to find the value for d, so if you just make d the subject, it becomes d equals to w minus u, right? So we need to find the value for d. Weight is basically the mass into gravitational accelerations, which is 35 into 9.81. I should write this answer first, like write the equation first. Weight minus upthrust. Upthrust is rho Vg, rho is already given, 1.03 into 10 to the power 3 into 1. Volume is also given, 6 into 10 to the power minus 2, and g is 9.81 again. This is rho Vg, and when you multiply all these things, you'll get the value as 181 Newton. Right, and as all the informations in this question were given in what, three significant figures, right? So sorry, the least one is two significant figures. This one, the least significant figure was 2, so you will also write your answer as two significant figure, which is 1.8 into 10 to the power 2 Newton. So this was the equation for 18a. Quite easy to work. You just got 5 marks for almost very easy calculations. Then for part 2, the drag force D on the object, obeyed the formula D equals to kv square, where v is the velocity of the object. We need to determine the value for the velocity where k is given. Just use the equation. The value for D was 181, so it will be what, D over k, entire thing under a root, right? D over k. So 181, 2.2, entire thing under a root, and you will get the value as 9.1 meter per second. So this is the value for the terminal velocity. For part 3, we need to give two reasons why Stokes' law could not be used to calculate the terminal velocity of this object. Because they never at any point said that the object was circular shape or spherical in shape. And again, the speed we calculated in this part was 9.1, which is quite a big value for speed. And at these values for speed, the flow is never laminar. It kind of becomes turbulent. So if the flow is turbulent, Stokes' law are not obviously applied. So the two rules are: object might not be spherical and the flow cannot be laminar when the speed is 9.1. Okay. Moving to the last part, part B, it says that to lift the heavy object from the seabed, a diver uses a lift bag. The diver used compressed air from a cylinder to fill the bag as shown, and when released, the lift bag and the object accelerated upward until they reached a maximum velocity. Explain why the lift bag and the object reaches a maximum velocity. Okay, so we need to explain that why the lift bag and the object reaches a terminal velocity, or which is a maximum velocity. This is because that when this combination of lift bag and object starts to increase, like starts to rise above the seabed, at first the drag force increases, right? At first only maybe like upward force is acting on this system, and due to this the object initially starts to accelerate, and when the object is accelerating, velocity will increase. When velocity increases, drag force will increase, and at a point the drag force and the weight becomes equal. Okay, and when the drag force and the weight becomes equal, the resultant force becomes zero, and this is when the object stops accelerating and maximum velocity, or you can also say terminal velocity, is reached. But as the question says maximum velocity, so you're supposed to use that term only. Do not use the terminal velocity, even though we are using the same concept of terminal velocity, but we're not gonna reuse that word, right? So the definition is again the same, that initially the object is accelerating, or a system actually, since we are working with lift back and object in together, right? So initially they are accelerating, which causes an increase in velocity. Due to this, drag force also increases. At a point, this drag force becomes equals to weight when resultant force becomes zero, and object or and they, right, that means both the lift bag and object, okay, and they stops accelerating and reaches maximum velocity. So with this, our entire unit 1 ends. I hope the entire explanation was clear for you all to understand. If you guys have any question, please leave it in the comment section. I will try to reply as soon as possible. Thank you for watching. If you guys like my video, keep subscribe my channel, and we have a Facebook page, Facebook group. Join in our group to get the screenshots of your answers, and also like our Facebook page to get the updates about our new videos. Thank you for joining.